much, Anthony, for the invitation to be here today and to talk to all of you about an area that I really believe is really important, is the role of knowledge integration in the area of bioenergy, but fundamentally in the evolution of modern universities. And I want to start basically with this statement from Wittgenstein. He said, the world is the totality of fact, not of scenes. And when we're engineers, we tend to think of the world about things. We're very materialistic, but we don't see a little bit more broadly what is the other elements that make our reality that are super important, particularly when we talk about knowledge integration. And now, my experience with knowledge integration started 35 years ago. Probably the first day I got into my undergraduate education as a chemical engineering in Cuba, and I have a meeting with the director of the Cuban Chemical Engineering Program, Professor Benaviera Bertrand, and he told me what he was expected of me when I graduated 5 years later. And he told me basically we want somebody. They were actually developing an experimental program. They wanted us to be somebody that contribute consciously to the development of the environment. So we wanted to be a positive force in any place we were. And in the process of doing so, we are going to learn and we're going to grow. If you realize there was no talk about knowledge, and actually fundamentally he was asking us, you need to act out of ignorance because knowledge will come later in your life. So that was a fundamental thought in the way Professor Riviera Bertrand was acting. And basically it tells us you need to build your will to act. That was basically the first thing to do. Build your will to act first, convert knowledge into tools. So knowledge was not, for engineering, was not something that you have there. It needs to be converted into tools that then need to be integrated into algorithms to solve problems. And that was a fundamental way he trained us. What the training was, Cuba has a long tradition of the students going to industries because they have full access to the industry. But he wanted to develop, he wanted the access to the industry to be really fundamental in the training. And then he used the strategy for process improvement as a fundamental strategy for knowledge integration at the career level. So the idea was that from year one, you will go to industry, you know nothing, and you're going to go there and you're going to see the industry not from the technical point of view, but the industry was an entity that has two dimensions, the cost dimension, the total quality dimension. And the technique was the tool, but not the center of your attention. So the idea here was that from year one to year five, you will follow this methodology, and you're going to go every year, you're going to be changing the subject. We're going to go on Thursday to the industry, or Wednesday, or Friday we'll have seminars, and every Friday we're going to follow this methodology from year one to year five. And that was fundamental. And why is important? Because you can see here an algorithm, and this is the algorithm of process improvement. It's very well known, but this is actually, the chemical engineering in the world don't use that. This is central to the training of industrial engineers. So he hybridized chemical engineering with industrial engineering. And in doing that, he was integrated knowledge at the discipline level. So as you go from year one to year five, and you were moving to different targets, you were introducing new knowledge as tools to, and your projects become more and more, your capacity to solve problems become more important. Now, also very important in his training was the fact that he needed to control the way you think. And he actually introduced a number of tools in as we went there. For example, the first step is what are the causes of the problem? So we actually try to use the Ichikawa diagram, and we do that very, very frequently. We need to actually generate ideas. And of course, we have to use the brainstorming sessions to generate ideas, but you also need to screen your ideas. And we were using the six thinking hats as a way to screen the idea. But the important thing is, as you attack the process, the big problem of improving the process, there were different steps. In each step, you need to have different tools, which fundamentally were the way you think. And this, for example, is a very interesting tool when you actually use different perspectives or different ways to look at the reality to actually analyze the solutions that you were proposing. We were doing that from year one to year five, and that was the center of integration at the career level, at the disciplinary level, the unit operation level. The algorithm of process the unit operation were integrated in the algorithm of process design, which is very traditional for chemical engineering. The fact here is that they decided not to have final exams, and what they decided is each of the courses will be evaluated with the final project, and the final project will evolve from year one to year five. as you were gaining new knowledge. And again, the integration was the algorithm that we all know, the algorithm of knowledge of process integration. And but the knowledge was integrated also at the course level. At the course level was integrated. When you get the course, you have this algorithm and you were following your training, because at the end, this is, for example, the algorithm that we receive for process modeling, and you were going from point one to point one. You were actually moving to that algorithm. So what did I learn from all of those? Knowledge integration typically happens with the creation and use of algorithms. This is really, really important to solve problems at all levels. These algorithms are very powerful educational tools. The integration was happening in people, was not actual algorithm, was algorithm that was used to train people. And they tell also something about the nature of our reality. The fact that algorithms are so critical in solving problems tells something fundamental about the nature of our reality. The basic building block combined in certain orders. And when I say the basic building blocks, it's the facts combined in certain order, not in any order. It has to be used in certain order to have an impact. If you want to play in society, you need to play with those orders. It's just like a Lego game. The pieces, independent pieces, has to be integrated. And that is the role of knowledge integrators. The role of knowledge integrator is to build algorithms that you will use to solve actual problems in the society. Now, what was my experience as a graduate student? It was actually very, very different experience as a graduate student. I went to Canada with a group of Professor Christian Roy, and he basically was also a knowledge integrator. He was somebody that was trying to build an industry. He was actually developing a company, Paroba. This is the demonstration unit, a vacuum paralysis reaction, and the educational project was highly integrated with the industrial problem. And at that moment, I actually saw, I learned a number of things. First of all, how powerful was that to be working directly with an industry. But I also learned that, my colleagues in the chemical engineering department were studying very simple systems, and were very proud of the tools they were using. We were actually studying very complex materials, bio-oil, biochar. We couldn't apply those tools. So there was a clear problem for us. We said, being in an engineering department, we couldn't have the promise of science. The promise of science is if you use all these tools that come from science in engineering, you will actually be able to develop technology. We couldn't, because the system was so difficult that you couldn't formalize that. And that was fundamental. Other thing is, and unless you were able to create explicit representations of the structure of this material, we couldn't do science. So that was, and also the university didn't like that. Basically, we have these traditional scientists that were basically, they didn't understand why somebody wanted to build that industry, why all of this was needed. The role of the university was to develop knowledge. And that was basically my experience. Now, why I decided to devote my life and my career to bioenergy? Because fundamentally, in this planet, we only have one green engine, and that is photosynthesis. No matter what people tell you about energy, there's no other way around. Bioenergy and photosynthesis is the only way forward as petroleum industry become actually as the price of petroleum increase over time. So why the green engine? If you look historically, and when I say historic, it's at the beginning of the Earth, algae and cyanobacteria are responsible for the atmosphere we have. Billions of years ago, algae and cyanobacteria were taking the CO2, were releasing the oxygen, and they were basically producing oxygen. And you see here, initial oxygen was used to oxidize the metals, and eventually we have so huge amounts of carbon was actually buried underground because of photosynthesis, mostly in the form of petroleum, which were lipid, and also in the form of coal from trees. But photosynthesis is still today. You see here the amount of carbon that we reduce in form of photosynthesis is much higher than the fossil fuel emission. The problem is that most of this carbon is going back in forest fires or in form of the natural oxidation of the biomass. So if we are able to actually build or actually use the green engine, which is photosynthesis, I think we're in our way to solve the environmental problem we're facing today. So my technological quest, because I believe there is no other way in the world to go but bioenergy, I basically focus in a number of technologies: selective carbonization and charred products, fast pyrolysis and bio-oil products, petroleum refineries processing of second generation, unconventional oil, and sustainable aviation fuels. This is the area I work in, and this is the area where I use knowledge integration. But in terms of science, I actually I'm working developing explicit representation of carbon materials so that we can actually bring the tools of science into engineering, and also atomic representation of pyrolysis oil. So the promise of science hopefully will be that we bring, if we're able to represent our very complex material explicitly, we'll be able to bring all these tools that science has for this. Now, in data of selective carbonization, what we have been doing is, the idea here is, if you have a plant and by photosynthesis it actually fix the CO2 from the atmosphere, if you're able to remove the oxygen in form of water, you're going to be able to get your biomass in the form of charcoal that is actually, or a carbon material that is actually a very stable form. So what we have been doing, we have been developing selective carbonization technologies with acid and pressure. And the idea here is, and we have been able to achieve, yes, close to 80% if you use sulfuric acid, but very interesting also if you use acetic acid and formic acid. Today, technologies, you need 4 tons of biomass to get 1 ton of charcoal. With these technologies, you will only need 2 tons of biomass to get 1 ton of charcoal. So we believe that with this we can actually fight global warming very, very, very well. And my belief is that yes, it is a, of course, we have been working on the science, and the science is how to get information that we have. When you can see here how we can actually control the reaction to do only the hydration, we don't have to want pyrolysis, and also how we represent those carbons explicitly so that we can actually move forward with all the modeling and using all the scientific tools. So selective carbonization is important. Why is it important for my state? Why I care? Because in my state, in the east side of the Cascade, every summer we have huge, it's very dry, so we have huge forest fires. So my goal is to develop a carbon pump by which all the excess biomass that is in this forest that is burning is actually brought. All of this is the Columbia Basin, where we have actually our agriculture. We have big river, the Columbia River. So if we're able to get all this carbon into our agricultural land, we can increase the carbon, the carbon in the soil, increase the fertility of the soil, and reduce our forest fires. So for me, it's really important to work in this vision, because for the west of the United States, that is really very important for our agriculture and also for the fires. The same thing happens with pyrolysis oil. How do I get to describe the chemistry of pyrolysis oil? Well, basically, there are limitations. You can actually get all the analytical techniques that you can, and still you're not going to be able to represent more than perhaps 50% of the chemistry of the oil. Why? Because we don't know very well what is the chemistry of the oligomers and how we put all this together. Well, there is a point where the chemistry fails. Basically, you use all your analytical chemistry, you get to a certain point. After that, you need to develop methodologies and your imagination to build the structure of the oil and then be able to move forward in the future. That's what we have been doing. We have been using, of course, all the tools that we have at our disposal, like GCMS, all the analytical tools, in this case, to analyze the functional group on the oils. And we are now, but still, when we do all of that, we get the analysis and then we don't know how to represent the oligomeric fraction that are more than 50% of the oils. For that, we are working, and thank God we have ICRMAs, or all the high resolution analytical techniques. And what is interesting here is that we have these lines that tell us how the oligomers are formed. And that is really interesting because it opened the door to something that we couldn't do before, how to assign the structure of those oligomers. So we have been working in the assignment of the structure of the oligomer, initially realizing that the oligomers can be described from the structure they need, a precursor, and then the reaction that happened to them. That has been, we are working right now, again, to try to develop explicit representation of the structure of these oligomers, taking into account the reaction mechanism by which they're formed. But the idea here is to develop an algorithm. Again, we come back to the algorithm. It's not about the knowledge itself. It's how you put them together to be able to do something, to be able to develop the simulators that the petroleum industry will use for those oils. So what we have here is we have data that you get experimentally, you get algorithm, you get explicit representation of the structure of the oil, and then you can estimate properties, and then you can actually go and use that industrially. So again, it's not enough for us to go to the lab to get all the knowledge. You really need to go and integrate that into a point. And the integration really also requires a lot of imagination, because there is a moment where the knowledge that you can gain by the analytical techniques really fails to you. Now, even if we are making all this development, still pyrolysis oil will not go to the market. I think we tend to think as scientists that we're the center of the world, and it's not the case. So what really need to happen, doesn't matter how much development we have in pyrolysis, unless those oils are used in petroleum refineries, the first technologies, and that's what the technology my professor failed. That's how most of the technology has not been going to the market, because we haven't been able to get those oils into refineries. So what we're really interested is in the processing of second generation conventional oil in petroleum refineries. And you will say, why? Well, in this case, it's important to see what is happening with petroleum. The petroleum industry is actually not coping with the increase in energy demand in the world. It's lagging behind. So if it was not because of the increase, but the bioenergy, by the biofuels that we add, or the additives that we add, it's not because we have electric cars, and it's because we have lighter cars. Today, the price of petroleum will be in the roof. Most of the growth in petroleum in the last, this is from 2011, has been coming out of unconventional oil. So unconventional oil are fracking and so on. Most of the conventional oil, the one that you produce in Saudi Arabia and so on, are actually being stagnant for almost, imagine right now more than 15 years. Now, why is this important? It's important because the production cost of the oil, not all the barrels of the oil are made equal. So if you look at the price of petroleum today, which actually changed a lot because there's a few consumer and producer countries, yes, you can have oil extraction at less than $20 per ton if you are getting this light oil from Saudi Arabia. But the oil that we're developing right now, the tar sands, have very little margin. So we see that with demand increase because of population growth and increasing quality of life, the oils that are more expensive are becoming viable in the market today. So first generation oil has been going. So we expect that the demand curve will ask for an increase, and basically new oils will come to the market. What are those new oils? What are these second generation new oils? We talk about lipids. Lipids are already there. We talk about biomass-derived oil. We talk about tire-derived oil, hydrothermal liquefaction oil, and plastic-derived oil. So all these oils will go to petroleum refineries, and we have technology providers. So how do we get those oils to petroleum refineries? This is really a question that we need to ask today, and it's not by the work that we do in the university. It's not the work that technology providers do. It is through knowledge integration. So we have technology providers. For example, this is the BTG, a two-step hydrotreatment process that you can easily integrate into petroleum refinery. You can also process those oil to the hydrocrackers. The question is, why it is not moving forward? It is not moving forward because we haven't been able to certify those oils. Now, if you look here, this is a certification process for sustainable aviation fuel. You have a SAF producer that basically says, I have a new sustainable aviation fuel material. So basically, I will go to an evaluation process. Then this will be, then the technology providers will analyze whether that fuel that you provide is actually actually comply with the fuel specification, and then this fuel will be tested in gas turbines, and then they're going to have a second report that will be analyzed by technology providers and so on. But if you look here carefully, what we have in this strategy for the certification of sustainable aviation fuel is basically also an algorithm. You have SAF producers, you have technology providers. How will it look if we talk about the certification of pyrolysis oils? Well, it will look very similar. So you're going to have, but here, who are going to be your technology providers? Well, the technology providers will not be the gas turbines, will be the hydrotreatment providers. So it will be UOP, Nested, Soy, BTG. What will be the producers of the oil? Will not be the SAF producer, but in this case, will be ENSIC, BTG, and other producers. And the users will not be the airline industry, but will be the petroleum refineries. So as you can see, here again, we have an algorithm that is general, that when you see applied to SAF, also applied to sustainable to bio oils, and it's exactly the same. It's a certification process. Unless you certify that, people are trying, oh, we're going to get my oil into a petroleum refinery. It will never work. You're basically working with the user. Nobody will put a SAF in an airline. That doesn't work. The way it has to go is you go to have a certification process where you have a technology provider involved with, and that is really what is needed here. So another area where I see when knowledge integration has been very important to me is in the development of sustainable aviation fuel and the study of the potential in Latin America. So again, I know nothing about that, but the United States is asking somebody that wants to work helping the developing nation to comply with basically they sign an agreement in Corsia they're going to have sustainable aviation fuel. And the question is how do we go how do we help a small nation, the Dominican Republic, Costa Rica, Colombia, Ecuador to do that? And here basically you have stakeholders, you have a dynamic on those countries that so how do we do that? So we get 4 students, we have 5 students from these countries, 2 from Ecuador, 1 from Colombia, 1 from Dominican Republic, and we bring them but we bring them with the idea that, although I don't know how much time do we have. Okay, we do that with the idea that although I don't know how to solve this problem, I have a section, I have a fraction because I know the technologies. Now we're going to train them to actually advise their government what policies should happen for the countries to be able to produce sustainable aviation fuel. So how do we do that? Well, again, we start from the point of view, I know nothing, but I have the will to impact. So, but we have in the United States a very interesting way, the way we train PhD students. And the way we train PhD students is we basically bring them, we have a problem, we form a committee, we bring the expertise, we get the students 2 years to learn all the tools that they need outside my lab. And then at the 3rd year, they come back, they will write an algorithm, which they're going to basically do their PhD dissertation. So with that tool in hand, we can actually address this problem. So what is happening here is we have roundtable. Those are the roundtable in Dominican Republic. We were early this year there, so we meet with them almost every year. And this is the PhD student that is actually shadowing, is working with the roundtable, basically providing the support that the roundtable needs to actually answer that question. Basically, the question is, what policies should the country introduce to get sustainable aviation fuel into the market? So in this case, we're using the student is our knowledge integrator. So how does it work? So you have a roundtable, you have an interdisciplinary team, you have the government, airlines, civil aviation authorities, sugarcane industry, waste management, independent farmers. You have everybody and everybody's talking. There is a lot of chaos. So how do you get them to actually act? Well, the idea here is that we need to actually know what the tools my students need to learn. So I get my students say, I know you need to know mass energy balance, techno-economic analysis, life cycle assessment, system dynamic, geographic information system, supply chain, econometric, and policy. Go and take all these courses in all the departments. It can be economic, it can be, I have good people, I have a great ecosystem where they can learn. And then the idea is how it puts together all this knowledge so that we can actually go step by step to do the work that allows me to get the problem solved. And how will they work with the industry? So this is really, really the way. The idea here is by simply focusing in the fact that I need tools, organizing a step to solve the problem, we can actually start addressing this big problem. But then once we get this kind of training, we say, oh, now we have an algorithm that can be the base for training anybody in the world. Because if you realize those algorithms are general, those are general algorithms. Once you develop an algorithm, you can train in mass people. So we are developing a master program in sustainable aviation fuel, which actually is based on the experience of these students that have already 4 years in our program. And what we want to do here, they will be basically common courses in the program. There will be 3 certificates, one in SAF production technology, one in SAF policies, law and system view, and one in SAF combustion in the fuel side of SAF. You put all of them and you have a master program. And the idea here is we want to train people that go back to their country to work with their round tables, with their people to try to design and to develop the industry in their countries. So again, what we have here is an attempt. We are not ready, but we are ready to engage. Why? Because nobody has this kind of training in the world. Nobody has, so we are ready to engage in developing those algorithms and those trainings. Knowledge integration also happens fundamentally also at the disciplinary level, writing books, but also happen in the training of the students. We have the case, for example, of a student, Valentina Sierra. She was here with you, and she was developing a technique to model carbon materials. I have a big concern. My concern is she's going to leave my program. She's going to go somewhere. The knowledge will be lost. So how do we train graduate students around the world to be using those tools in their PhD training? Because as you remember, my discipline needs that. So what we did here, we worked with a number of our partners. We have here our friends from the University of Lorraine. We actually developed a global lecture series on biochar, which is exactly that. We put the expert in a different order. They're going to come, they're going to be teaching, and we're going to be training together our students anywhere in the world. So those are initiatives. The same thing is with the conference. Many people go to the conference because they want to present their work. That's not the way I go. I go to the conference because I want to see where is the field evolving, and I want to integrate knowledge. It's also a perfect place to integrate knowledge. So with Dr. Dufour, we work in a paralytic and biochar conference when we organize every 2 years, which is actually a good way for us to come together and see how we're evolving. So fundamentally, knowledge integration is actually very, very important. Now, let's talk about knowledge integration in the creation of new engineering programs. I should say that engineering disciplines are fossilized. If you see today, the way we're teaching engineering is actually the same way that was teaching in 1950. There have not been much changes in the teaching of chemical engineering, for example, the other discipline. So let's look at the dynamics. When you look at the fundamental sciences, they have a machine, and it's very clear how it works. Is the machine of knowledge creation. It's a scientific method. So we have this is basically a machine that works and it generates knowledge, and that's how we actually do science. We have the machine of knowledge creation. But when you look in the applied sciences, which is what we do, these disciplines have been historically integrated, and they have been historically integrated in applied disciplines like computer science, engineering, etc. So how this process of knowledge integration happened historically is very important because it has a stoppage. I mean, we have not been doing that in the last, let's say, probably, or we have been doing that very slowly in the last few years. If you look in the case of chemical engineers, in the case of chemical engineering, you have the fundamental science that was basically synthesized, the science of chemical engineering, and then we have the unit operations where they basically come together. And this process, fundamental process, integrated into generalized strategies for analyzing, is actually something that needs to continue. And we don't see that. Unfortunately, the chemical engineers has going towards the idea, in my opinion, a wrong idea, that if they actually master the fundamental, the phenomena, automatically it will have an impact in the industry. This is a big mistake. This is not, there's not just an automatic impact from the phenomena. And in fact, the character of the engineer is integration of knowledge. When I see departments that are only doing fundamental science, they're basically this deserves to the engineering discipline. Engineering discipline is fundamentally integration of knowledge. So what happened in the case of biomass resources? In the case of biomass resources, it's a big problem. Chemical engineers are ill prepared to address. And actually, the reason for that is because they only, the materials that they study are very simple. They don't have a structure like biomass or other biological systems. So we really need a new kind of engineer that is able to develop the bioeconomy, the circular bioeconomy. And for that, we need to be seeing how we're going to do that. So we do that very opportunistically. We're working with the University of Filipinas, Los Baños. Here we have a very good opportunity because they have a chemical engineering program and they have two specializations. One is sugarcane and sugarcane processing because they have historically very important sugarcane industry, and they have one in pulp and paper engineering. The question here is, can we actually look at the training on the sugarcane and the pulp and paper and see generalized strategies that could be synthesized to develop a new kind of engineering for bioresources systems engineering? And that's what we're doing with our colleagues of the Philippines, looking at their courses, saying, okay, how can we actually use all this knowledge in good chemistry, in good structure, morphology, to actually train somebody with that sensitivity so that they can eventually come and address the problems with municipal solid waste. So that is a work in progress that actually is very interesting to me. Without having an army of engineers, we'll not be able to address the problems that we have today. Now, I'm department chair, so I also have a big responsibility in knowledge integration in my department. So my department is a biological system engineering department at Washington State University, and we are a department that we could not maintain our undergraduate program because we didn't have enough students. So we really become a graduate program. And a graduate program has four distinctive areas: agriculture, automation, engineering, food engineering, bioenergy and bioproduct, and land and water resources. Uh, our program really today is actually very high ranked. I mean, if you look at academic analytics, we're the most productive research program among agriculture engineering programs in the United States. So basically, it is a program that mostly trains PhD students. We are located across the state, so it's very difficult to see us, but we have a relative large fingerprint that goes from laboratories, very much like chemical engineers use, to all the way to field studies and robotics in field studies. So for us, but our department is fundamentally, when you look at the point of view of the training, it's a traditional PhD program where you get graduate students, and eventually we have 58 PhD students and 9 master's students. So we want to evolve. So how are we going to evolve my department? Well, initially I told you that we are introducing online master programs, and the online master program we have graduate students that can come from anywhere in the world, and then we want them to be the basis for our traditional master program, because for us it's very expensive to the way we train our students. We get 2 years full of courses. So if they could pay the classes early, and then they come into the program with already a number of courses done, it will actually be very helpful to us. So as I told you, today we have a lot of activities that are actually happening. We do a lot of things, but actually it's like heat. We release a lot of heat. We are traveling in many places, but how can we actually do something more focused? The department can grow. Of course, again, we're building 2 online master programs that should start next year, and the department will look something like that. But as important as the development of master program, we want our students to be able to go to top world-class laboratories. Actually, training the students in our university. I mean, we have a very good academic environment, but we really believe that the students should be trained in the world. So we are here at the University of Lorraine, and we're very thankful because many of our students have been able to come to this top world-class laboratory. But for us, when we design a program, we should not be thinking what equipment I have in my lab. I should not be thinking what equipment I have in my university. I should be thinking what equipment are available in the world, and we should go to the world to do our studies. And that's my vision. Our design of a program should not be limited by the limitation of our laboratories. And that's the reason why I'm here, and that's the reason why we have been building our relationship with the University of Lorraine. But it has to evolve. It has to evolve in which all this knowledge is actually condensed into tools. I mean, we need to actually be looking at all these papers that we publish in a year, how they are part of a toolbox. They need to be actually building a toolbox that later is integrated into algorithms, and these algorithms are later integrated into new online programs and also working with the stakeholders. We need to get to that point. We need to get to that point in which knowledge that is formed is actually condensed into tools, it actually is integrated into algorithms, and we need to be working with our stakeholders the same way we do with our Latin American friends, so that our impact in society increase and we actually engage. So that's really our vision of what we want to build. Our department today is only this, and we're gradually building all the other components on this algorithm so that we have a machine. Our department is to be a machine that is impacting society, and this is the way we look at that. So, but we don't have undergraduate programs. So for us, it's always a question: how can we contribute to the formation of undergraduate students? Well, that's also we are also very interested in engaging. I mean, if you look today at the universities are in big trouble. Knowledge is very cheap. The students can gain knowledge anywhere in the internet for less than $100 a course, and they can actually get tutors in India for very good tutors, excellent tutors for less than $10 per hour. The question is, how can we leverage the uh, university's rich intellectual ecosystem to create a new value proposition for research, teaching, and extension? What we have essentially is an ecosystem. How the students can leverage that ecosystem, and we believe that there are opportunities to actually do something similar to what we do in graduate education. So, and students come with the will to change the world. Can they encounter advisors and industrial stakeholders when they can actually work with them? Can we work together to identify courses? Can we create an algorithm to solve this problem? Can the student use that algorithm and guide them in their graduation process? So we're really interested in engaging in that new kind of it can be very close to chemical engineering program, it can be very close to mechanical engineering program, or it can be really in the middle of many interdisciplines because that's what requires the kind of program. But fundamentally, what we should not kill the will of the students to contribute. That's why when Bill Gates and others leave the universities, you say, how is it possible that we could not keep those kids in our universities? Because we kill their will to solve problems. And we basically say, you need to gain knowledge, 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 and then with knowledge you're going to go outside, sometimes pretending that you're very good, and then basically try to find the place where you're going to solve a problem. I think we are in the situation today when the educational system has to change and has to actually be driven by the will of the students to solve problems and in the process to help the students to educate. And my department is in a very good position to do so. So when we look at knowledge integration, it also needs to happen at the level of modern universities. And when you're basically looking at knowledge integration in when you look at the modern universities, the departments, people don't talk between them. I mean, it's sad, but in many places, people are so focused in their disciplinary area, they're just so focused to get money from the funding agency to keep. I mean, it's sad to say, but we are living in a survival mode. It was never, I mean, academia was never meant to be a survival mode. Faculties are trying to survive. I have 10 PhD students, I need to find the money. And that scarcity mindset is actually undermining universities, the development of the universities. So the rate at which universities are integrating knowledge is too slow to address the needs of a rapidly changing society. So how do we actually accelerate the integration of knowledge in modern universities? And we have the case of the University of Pennsylvania. They're trying to build an interdisciplinary school. The rationale is they try to find solutions to numerous societal challenges that would require working together and pulling from this disparate field of knowledge, specifically training our students on how to do so is critical. But again, what I'm trying to say is interdisciplinarity is actually okay, but it's not enough. You can have people from different disciplines unless they're able to build an algorithm to form a problem, to solve a problem. Unless the tools are used in certain order to solve the problem, the impact is really very, very, very slow. But we're seeing a growing interest to actually develop a machine of knowledge integration at the university level that could eventually result in more programs, in more graduate programs, or in more online programs, and so on. So why university-wide interdisciplinary school? Well, to coordinate growth of courses and curricula around engaging interdisciplinary areas. We need people that are able to go outside the university to engage with with the society, to actually create these roundtables and bring the professors and the students and making that an educational experience. Anything we do in the university should be an educational experience. It is not that only when we go to classes and education experience. Everything that we do, and that basically we try to be scholars, which basically means trying to bring all the tools and the logic into the solution of the problem or to the creation of new knowledge. It should be actually very important. A school specialized in knowledge integration for teaching, research, and outreach is really important and needed in the modern world. Well, the conclusion is we need to develop knowledge integration machines. They will play an essential role in the evolution and growth of the university of the future and bioenergy. In the case of bioenergy, we're not going, I mean, the role of the academia is to catalyze the field, but it would be a mistake to actually go outside the society and say, we're going to solve the problems, we're going to develop the bioenergy from our lab. It's not possible. It's not our role. Our role is to catalyze the process, to say this is our function in the game, but here we need to actually work with the society and basically the roundtables, the industry, to be able to uh, to to get to get the industry to grow. We should do knowledge integration at all levels, from the graduate education, research, and outreach. And knowledge integration should happen in people. It's not enough to have this algorithm there where you put them. It has to be the basis in which you create people. And by repeating this algorithm, it becomes habits. So that's really the importance of knowledge integration. When you have algorithm and you force people to repeat those algorithms again and again and again, it becomes second nature to the people, habit that allows them to actually improve. It is the most efficient way to leverage existing assets to increase societal impact. I would say that universities need to actually go back and question the role they have today. The universities today will not survive, cannot survive. Society cannot continue supporting this kind of universities. So it is absolutely critical that we go back and we actually redefine our role in the time of artificial intelligence. What is really valuable? What are we bringing to the people? But people are not coming here to learn knowledge. People are coming here to savoir faire, to be able to do things. And that's what the students are. And many of our students come to university and we kill their will to do. And we basically are always pushing knowledge and knowledge and knowledge. And it becomes so disgusting for them that but unfortunately, the best of them, many of the best, leave the university. So knowledge integration is a skill our students need to receive from the undergraduate education. It's my experience, and it has served me in my whole career for more than 35 years now. With that, I would like to thank my students because they're my big teachers. I should say that well, I engage in these processes because I learn. They go and they teach me many things, and hopefully I teach them something. But it is really symbiosis. It's not that me. I'm basically. I look at another one of them. One of the students engaging in this process. The only difference is that they have 30 more years ahead in their life. They probably have only 15 more years to go in this career. So it's time for us to give the torch. But but what is exciting, what's really exciting is the experience to engage in solving a problem, the experience to be a student in the process. And that's, I think, how academics should look at their role. They should not be, I mean, we are all learners, and that's the way I look at myself. I want to thank, of course, our funding agencies because, as imperfect as they are, they allow us to do what we want to do. And I think it's our responsibility to make sure that every dollar that taxpayers spend on us is well used because there are certain needs outside. There are people that are starving, there are people that need homes. So when they put money in the universities, we need to make sure that our impact is the highest we can. With that, I would be very happy